So now that we have seen how the hardware implementation, the RTL implementation corresponding to a smart timer could be done, I am going to just very quickly review some common behavior patterns that are used as part of implementing register interfaces for different hardwares. The most common and obvious one that we can think of is I want to have a read-write register. I want a register into which I can write some data, and then when I read back from the same address, I should get back the data that I wrote. This, for example, is exactly what we did with the register bank, right? Now there are a couple of variants on that. One is that I might have certain registers which are read only. In the case of the smart timer, we saw that register at address 0xc was a read only register because it was basically status bits. Now the interesting thing is you can also have a concept of something called a write only register, and what that means is you can write something into that location, but when you read back there is no guarantee what you will get. An example of this might be, let's say that you are trying to transfer data out of some, let's say a UART or an SPI or something of that sort. In general, when you write something into the write buffer, when you read it back, there is really no reason to give you back the same data that you wrote last, right. So in some cases what they do is they either return something completely unrelated to what you wrote, or they just always return a 0 to indicate that this is a write only register, it is not something that you should be trying to read from at all, right. What is important in all of these cases is that what are the reset conditions, especially for read write and read only registers. Reset, you only really care about what happens when you are reading from it. Well, you might also care about a write only register, what happens when it starts up, right. Are you required to write something to it, or will it just take the whatever value you need by default, right, is something that you need to know, because unfortunately if it is a write only register you can't read back and check what value it had, right. Write one to clear is also something that we saw, right. It had a very useful interface in the context of the status wrap signal, because it basically says the status wrap can be sticky, it gets set to 1 and remains 1 until we explicitly clear it from software. You could also, instead of write one to clear, you could also have a write one to set, which just does the opposite, it basically sets a value to 1, right. And what is potentially more interesting is you can actually have write one to toggle, right. Now why is this useful? Primarily for GPIOs, right. You can actually say write one to toggle and say every time I write one to it, this is like a toggle button, right. Every time I press it, the state changes. And by writing one to toggle it, you can basically say, okay, I don't have to read it, mask it, change the value and then write it back. I just write one to it, it inverts the state. Why is this useful? So for example, let's say you actually wanted to create a kind of a waveform, maybe a pulse width modulation purely in software, right, or even a clock pulse kind of a behavior purely in software. Of course, it would be slow because it's going to take many clock cycles to generate each of these different pulses, but it means that you can completely control it from software and you don't need to care about what is the present value of the GPIO and do I need to invert it or not. You can just basically say, okay, each time I send a pulse over there, toggle it, and it makes certain kinds of logic and certain kinds of what are called bit banging protocols that are used for bit banging implementations of protocols, right. So a UART, for example, could be taken that way, where I take a GPIO and directly just force the bits to ones and zeros as required in order to get a certain speed or a certain form of data transmission. Of course, it would be slow, but well, UARTs are slow, so it is okay. Now write 0 to clear and write 0 to set can also be done, right. There was nothing specific about writing 1 for all of this, but they are rare, they are not generally used because a write 1 is considered a more explicit indication that you are actually trying to do something over there. If you are trying to write 0 to clear or write 0 to set, then you need to make sure that it is documented properly. There are a lot more behaviors. As I said, you don't necessarily need to write. If you go look at the Verilog code, you will see that potentially I could have added logic in my read part of the Verilog functionality, which says if this particular address is seen, go change the value of one of the registers, right. Why wait for a write? I could have also done it based on read. This can be useful, as I said, for certain kinds of flags. You set a flag and as soon as somebody has read the flag, it basically clears the flag, right. You do not necessarily need to hold it over there and keep it as 1 until it is explicitly cleared. But it can also be tricky if there is a chance that you are going to be reading it from multiple different locations, because then whoever reads it is going to end up clearing the flag and you will not really know how that happened, right. So, it can be done, you have to exercise caution when you are using it. Self clearing pulses, we saw the W1P for the reset pulse, right, and reads in this case will basically return 0. So, they are not going to return the value that you wrote into it. Sticky until reset, right. So, this is going to be something even beyond what it is not necessarily something that was even written from the software. What happens is that if there is a fault somewhere in the system, a bit gets set to 1 and thereafter any time that you try reading it, it will basically return a 1. And in fact, sticky until reset could potentially mean that there is no way of actually clearing that bit through software, because it is actually indicative of a fault in the underlying implementation or in the underlying hardware, and the only way of getting around that is pretty much reset the entire system. You can also have a lock which says that I can do something like sticky until reset, but rather than being set by a fault, I can set it through software and then it will remain over there until I actually switch off the system or reset the system. Now, where would I use this? For example, certain kinds of configuration information where I do not want it to repeatedly change. The very first time that I am switching on the system and the first code that I run, maybe during boot, is going to set a few values in some registers, and thereafter I cannot change those values until I have actually reset the entire system. So, this can provide you with some interesting kinds of protection mechanisms, right. Let us say that somebody wanted to write code that in software would go and change certain configurations. You do not want to allow that. You can have it such that the very first time, as soon as the system is switched on, the values get written in, and after that you are not allowed to change them without restarting the system, right. Now, there are also aliases that you can bring in over here. You can have things like reg set and reg clear. And why is this important? Because normally if I wanted to set a particular bit in one register, or in a 32-bit register, what I would need to do is read in all 32 bits, mask 31 of the bits out so that they are not affected, and change the value of one particular bit, write the result back. This is what is called a read, modify, write operation, right. I first have to read back 32 bits, modify one of them and write back all 32 bits. That way I can be sure that all the other 31 bits remain as the same value that they had earlier, just one bit alone has changed, right. So, this read, modify, write turns out to be a common kind of occurrence because we are trying to pack many different functionalities into a single 32-bit register. The problem is there is a notion of what is called a hazard, especially in terms of what is called atomicity, right. We sometimes want what are called atomic operations. What happens in an atomic operation is that I want this change in the particular bit to happen pretty much instantaneously. I do not want it to read, modify and then write, because there is a possibility that between the reading and writing, one of the other bits has actually changed its value, right. So, to ensure that I have an atomic update of one particular bit, we want sometimes to have alias kind of conditions which allow me to directly set or clear individual bits in a register. Now, the functionality that we have shown so far does not directly allow that, but if you think carefully about how the writing and the reading handshaking works, you can probably imagine how would I extend my module so that I can directly allow setting or clearing individual bits inside individual registers, and can be very useful in certain conditions. The other thing is shadowed updates. This is again something that we actually saw in the case of the smart timer, right. We had the active period and the active duty cycle, and we did not want to change them in the middle of a counting process. So, what we said was you either need to disable, that is change the control signal to 0, or you wait until it has wrapped around, and at that point you can accept the update. And that was done very cleanly. We did not have to make any other changes in the hardware. The shadow registers get updated immediately, but the active registers wait for and check whether there is an update pending, and if there is an update pending and it has wrapped around, it immediately goes and changes the active values. There can also be scenarios where your register bank is in turn something which is trying to set a larger number of registers behind the scenes. Examples of this could be a place where, let us say, you have a fairly, maybe a long, a filter, coefficients corresponding to a digital signal processing filter that need to be stored somewhere in the memory of a hardware filter module, and rather than just trying to implement this whole thing using by assigning a separate set of addresses to each and every coefficient in the filter, you might decide to have an indirect way of addressing it, where you say that I will provide some way of modifying individual values in a larger table by using some separate writes into individual registers that are defined appropriately, right. So, it is rare, but there can be scenarios where you want to modify such large tables, and you sort of do this in an indirect manner rather than trying to take that entire large table and put it into the address space corresponding to the peripheral that you have. So, in general, when you are designing, right, as a designer, when you are trying to go through and build a system, there are a few things to keep in mind, and this, even though I call it a checklist, it is just some good practices to follow when you are looking at it. Always define reset values. You need to know what is going to be the state of the system immediately after reset. If it is not important, make that also explicit and say that you cannot rely on what the value of this is going to be after reset. For example, we saw that in the case of the ARM UART, right, there were some bits that were not specified after reset. What that means is you should not rely on those values being 0 or any known set of bits immediately after reset. And if you have reserved bits, then it is generally a good idea if you can ensure that they are going to be read as 0 and that writes to them are going to be ignored, right, because even though I said that from a software point of view you should not be accessing those bits, it is possible somebody will do something that you do not expect. So, you ideally do not want the entire system to fail if that goes wrong. By honoring this WSTRB signal, right, it sort of helps us with alignment. We can actually use this in order to decide whether or not I need to write into individual bytes. We saw how the WSTRB was used, for example, to decide whether I was writing only into bit number 0 of to clear, for example, right. Use pulses appropriately, right, avoid latching write only bits. When I say write only, this is like the W1P that was used for the reset pulse, right. They are very useful, but they are for specific actions and not for setting state inside the system. Sticky status is a very useful thing again, and clearing it by using W1Cs is also write one to clear is useful. And the shadow registers, as I mentioned just now, are very important and useful for atomic updates, right. In general, you might have noticed from the Verilog code that we saw, the decode was relatively clean and simple. We just had to look for a few address bits corresponding to each register, and within that the extra logic was fairly simple. At best we would need to check for the value of the update enable signal or update pending signal, check whether there are some strobes or something that are active, and that is about it. We do not have any complicated logic. Why is that? Because we typically want this bus based interface to work at relatively high speeds. We want it to be designed in such a way that it is simple and it can interface with processors that are themselves going to run reasonably fast. Okay. So, to summarize the whole purpose of using register banks, by clean use of register banks, we can turn data paths. You saw what the PWM core looked like. It did not have anything to do with software, right. But by putting it inside the context of a AXI wrapper, right, we were able to turn it into a usable peripheral. And what I mean by usable is not just in another hardware block, I can actually control it from software. And by using the basics of AXI Lite, so far we have looked only at AXI Lite, and for a large part of what we are going to be doing, we will be concentrating on AXI Lite, right. And by sort of using some fairly well disciplined register behaviors, all the pulsing for resets, the sticky bits for status and so on, we can get a very robust kind of memory mapped I/O interface. And as we just saw in the case of the ARM datasheet, real datasheets use exactly the same kind of patterns, right. They also use write 1 to clear, they use pulses, shadow registers and so on. So, I would strongly recommend you look for examples of this, right, try to find out more scenarios where you can see similar kinds of behaviors in datasheets that are publicly available.